All right. Well, thanks, Aya, for the introduction. My name is Dehowe Feng. As she said already, I'm a software engineer at Bitnine Global. I've been here for around 2.5 years, and I work on AgensGraph and the development related to that. And let's get started. Okay. Well, first of all, what is IMDb? Well, IMDb is the Internet Movie Database for those of you who might not be familiar with this. It stores information about movies, TV shows, actors, actresses, etc. It's basically everything related to TV and movies. And right now there's something like 6 million titles and 9.9 million personalities stored in the IMDb database, and this number is growing daily. The dataset is constantly being updated. I think every week it updates, and yeah. So next, what is IMDb Pi? Well, IMDb Pi is a Python package that's used to manage and retrieve data from IMDb itself. It's written in Python and C. It's maintained by some dude on GitHub, and it retrieves data either from IMDb's web server or a local copy of the whole database if you have that already. And it's we use it personally to import the data into the relational databases. And the key player in the IMDb Python package is imdb2sql.py, which we will talk about later. And Aya already went over this, but I'll quickly go over it again for those of you who might need to hear this information again. AgensGraph is a hybrid multimodal database system that supports both the graph data model and the relational model. And we use both SQL and the Cypher query language, and we're a fork from PostgreSQL. Right now, the current release is a community edition, version 2.1, and you could download it off of our website, or you could check it out on GitHub and get the latest commit. And right now, the features we have are Cypher plus SQL integrated querying, as well as Cypher and SQL alone. The graph features a vertex and edge hierarchy, which means that the graph data is structured like such so as a graph. And we're optimized for fast graph traversal, as well as business intelligence analytic queries. And we have support for many different client libraries like JDBC, ODBC, Python, Node.js, just to name a few. And yeah, so I'll quickly go over the Cypher query language for those of you who might not know what it is. It's a structured query language written for graph databases. It's a declarative query language for the property graph model. It follows kind of the match where return format, where SQL follows the select where from. And I'll show you an example later to kind of illuminate that for those of you who might still not know. And it's a way to query nodes and edges in a graph, pretty much, developed by Neo Technology in 2011. And if you want to check out more information about the Cypher query language, you can go to opencypher.org, which is run and maintained by Neo4j, and just maybe participate in developing the Cypher query language. They have other resources there to help you learn. And yeah, here's a quick Cypher example. Well, as you can see, there's a Cypher query below. It's follows the match where return kind of format as we discussed earlier. And you can see that the match kind of has like an ASCII art type thing. We're looking for a person who loves a dog. And you can see that the parentheses surround the nodes, which makes it clear that they're nodes, and brackets surround the edges, as you can see, are colon loves. And then the colon labels, the colon denotes labels pretty much in this graph. So like it gives information as to what your node or your edge might be. And here we're looking for dogs that match the name Dehowe. So dogs or relationships between me and dogs, I guess. Yeah. So the return statement has we want to return my name, Dehowe, or name a node that matches the name Dehowe with a label R that points to dog, and we also want their name and their age. So here in the result, you can see that Dehowe loves Pokey, age 3, and Dehowe loves PQ, age 7, is our return result. So hopefully that kind of shows you how Cypher works in a very, very simplified way. Yeah, so now I'll talk about how data is stored in this relational schema. Well, the data is normalized and it's stored across 21 tables. The information is pretty spread apart, as you can see, since the data is normalized. There's a bunch of arrows pointing to the tables that are related to each other, and we need multiple joins essentially to find information across the tables if we want to query them. And here's a blown up version of that table that I showed you earlier. Maybe commit this to memory. We're gonna keep talking about this later. So yeah. So from this table, we can make some key observations here. There's 4 main entities: keywords, companies, persons, and productions. You can kind of see them in the table that I have here. And each of these tables have their own set of tables. I mean, each of these entities have their own set of tables with relevant information relates to them. So we can see that connections are very important in this database. Persons will have relationships to productions, and keywords will also have relationships to productions. Companies will have relationships to productions, and productions will also have relationships to productions as well. So like, yeah, I guess who would have guessed IMDb productions are the most important thing in this database? So yeah. So when we want to talk about IMDb in a graph database, you can see that the 4 main entities we discussed earlier, keywords, companies, persons, productions, these will become nodes in our database. And all of the information related to these nodes will be stored as attributes within the nodes themselves. So all the information in those tables that we saw earlier will be kind of denormalized and condensed into the tables that have the nodes, and the relationships between the nodes will be defined as edges, and they will all be stored internally as JSONB. So here below, I have kind of a very simple example of what I'm talking about. You can see that there's a person node here with the name Matthew McConaughey, and there's an edge that's pointing to the production node, which is has the title Interstellar because Matthew McConaughey was the actor in Interstellar. And then off to the side on the right, I have kind of some information that might be stored in the person node. Well, for Matthew McConaughey, you can see his name is there, ID is there. The ID is kind of like the link, they're like his the URL information on the IMDb website. You have his gender, male, and his birth date. There might be other things included, like maybe some fun trivia or like his height stored in this node as well that I didn't include for the sake of space. But data for IMDb is pretty rich and has a lot of information regarding these things. So yeah, here is a picture of the schema of the IMDb graph database. As you can see, the kind of, rather than having 21 tables, now we have 4 kind of nodes with the information stored inside. You can see that keywords has a few bits of information stored, and productions have things like the title of the production year, movie ID, status ID, maybe things like if it's like a TV series, it has the number of episodes or like the number of seasons. And in the person nodes, you can see there's things like name, ID, maybe like the pronunciation codes for their surnames and first names. And then there's nested info that might be included if it exists in the nodes as well. Companies have information like the name or the company type or maybe the country where the company might be from. And yeah, as you can, so you can see that there's the 4 main entities as well as the edges that kind of connect them. So keywords, of course, are going to be keywords of productions, and that's kind of denoted by the edge keyword of. For persons, you can see that there's edges like actor in, actress in, producer of, which will kind of denote what type of role they might have played in making the production. And companies have similar edges as well: distributed, produced, did special effects for. These kind of say what type of work that the companies will have done on the production itself. And then productions also have an edge that leads into itself. You can see there's follows, followed by, remake of. So these kind of denote the relationships that productions might have with each other. So maybe a production is like a sequel of another one or something. Yeah, there's lots of different type of relationships in this graph, and there's basically edges that will kind of denote all these different relationships. So yeah, IMDb in a graph database is you can see the graph schema is a lot more simplified versus the relational schema. I personally feel it's visually easier to comprehend than having 21 tables with information all kind of jumbled and spread apart. Rather than trying to query across the table with joins, the information can be accessed from within the nodes themselves. So you basically just need to match the node, and then from there you can just get the information rather than querying across the tables with joins and stuff. There's definitely like an emphasis between the relationships between the nodes in this database. So in the table below, you can see that in a relational database, entities and relationships are both rows in a table, whereas in a graph database, the entities will exist as nodes and the relationships will be like, well, relationships or edges. So overall, definitely more visual in nature. Now I'll talk a little bit about how the import is accomplished. Well, first, we have to retrieve the data from the IMDB FTP site, and I could use, if you're using like Fedora or like any type of Linux system, there's like the command below that you can use, just copy and paste, or this will all be on the GitHub as well for those of you who need it later. And then the data is imported into AgensGraph as a relational data using the IMDB2 SQL.py, and there's like the kind of command that you can use there listed below. And then after we import the data into AgensGraph, we use this, the shell script that's also included on the GitHub to convert the data to a graph format. And we'll talk more about that more in detail later. Yeah, the data transformation for IMDb Pi is basically separated into two separate phases. There's the data consolidation, where we kind of manipulate the data to kind of be ready to create a graph. And then, of course, after we do that, we create the graph creation. So there's advantages of having both the relational and graph data models in our AgensGraph. And below, there's like kind of a quick little flow chart, and you can see how the data is to be finally graph data. Haha. So now the data consolidation part. So when we first want to kind of transform the relational data to be more friendly to be transformed to graph data, we create views to like kind of denormalize the data. So here's an example query below of how we did it. We kind of, for people, for the person's information at least, we selected information across the tables and then we joined them together. And then we use these queries to create 4 tables that represent the 4 major entities of the graph schema. And the graph ready tables contain one column pretty much that holds the JSONB objects that are complete and ready for import. And the data is stored as JSONB because it's semi-structured, which means that if a field exists, it'll be there. And if it doesn't exist, it won't be there. There won't be like a field and then like a bunch of nulls for things that exist but aren't there. In that sense, it's pretty lightweight. And there's also the ability to kind of nest JSONBs and nest more information if that's necessary. Here's a sample JSONB query that we use to kind of prime the graph to be ready for import. You can see it's really long, so we had to get basically all the information related to people across all the tables for the people. You can see this query is huge. There's a lot of joins and stuff that we needed to do. So select from. Yep, and then part 2, the graph creation part, I will discuss now. So when we create the graph, we need to kind of set the graph path. And here is an example of how to do that below. So we create graph, IMDb graph, and then we set the graph path to IMDb graph. And then we create vertex labels for each entity. So create vLabel if not exists person to create the vertex label. And then the AgensGraph custom load statement loads data from relational tables to graph form. So here is an example of that statement below. Load from JSONB_person as persons, and then we create all the nodes in all the person nodes in the graph at once with the following statement, create statement using the load statement. And then after that, we need to create property indexes for basically everything, all the nodes that we brought in, because we need to reference the the ID values in the graph for the edge import later. So just being able to index that will make that process a lot faster for us. And then after that, the edge labels are created for all the relations as well. So we create edge label if not exists for actor and producer of, writer of, etc., etc. And after we have all these, the AgensGraph load is used to get the tuples from relational tables that define the connections and then we create edges between the nodes in the table. So here's an example of a statement that we use to create all the edges. As you can see, we're using the ID value that we talked about earlier in the where statement to kind of match across the tables the information that relates to each other, and then we use all this information to create the edges. So here you can see we're creating all the producer of edges. And yep, the match where return statements are used to iterate through the table to find certain type of edges and then draw relationships between nodes together, and it's pretty long process. So now that we've talked about how to do the import itself, well, how can we really use this information? We can query the graph in various ways to find out what you want to know about actors and actresses and productions and stuff. And it's kind of great for examining connections between productions, actors, and companies, and basically anything that you might want to know about movies. And next, I will show some sample queries that could be used with this data set. So yeah, example one, query one, say you want to find all actors that acted in the movie Inception. Well, here's a quick Cypher query that I'll go over. So we'll match all the persons that was an actor in a production where the title was Inception and the kind was movie. And then from there, we'll return distinct names and titles that we matched in our match and where statement, and then we'll order the names by ascending. And then so our SQL query will kind of do the same thing. There's the equivalent SQL query below. So we'll select the name and the title from the title table T, interjoin to the cast info table, interjoin again to the name table, which is these tables hold kind of the relevant information we need to find the same information. And then our where statement is you can see we're matching every title that matches the movie Inception, where the kind ID is 1 and the role ID is 1. So I guess in the relational IMDB data, all the information like whether a person was an actor in a production or like what kind of movie it is, they're all stored as kind of ID values like 1, 2, 3, 4. So in the graph data, I kind of took all the ID values and just put the corresponding like actual label in itself. So like 1 is actor in, 2 is actress in, and et cetera, just so the information would be more meaningful to read, just as an aside. So anyways, after we query, we can see on the right, we have a result. You can see that all the actors that kind of worked in Inception are listed there. I truncated the data just for brevity's sake, but there's like 56 rows of actors in Inception. So yeah. And now in our second example, we will talk about we want to find all the films that Leonardo DiCaprio has worked on. So not just Inception, but what other movies. So our Cypher query below will be we'll kind of follow a similar format. We'll match the person with the relationship to a production, but this time we don't specify the label for the relationship. We just kind of want to know all types of movies that Leonardo DiCaprio might be connected with. So the where statement is similar again. We want to find where the name is DiCaprio, comma Leonardo, and the kind is movie, and then we return the name and the labels, and then the title of the movie again. So in the SQL statement, you can see that we have another join now because I guess we're looking for a more general form of the query before. So we have to kind of add another join to find that information because we're also interested in the role that he might have held in the movie. Here's the result of the query, I again truncated it just so it fit in the slide. But you can see that not only was Leonardo DiCaprio an actor, but he also was a producer of a lot of films as well, and a writer for one film, interestingly enough. I mean, this information might have been updated more, but he's not only an actor, but like also does other things related to movies. So I guess this is interesting for seeing if you want to see if a person might have done things besides what they might be known for. And in our third example, we want to find all actresses that have worked in films with Marion Cotillard, and below is our Cypher query. You can see we want to match a person that was an actress in a production, as well as another person that was also an actress in the same in a production as well. So we're kind of hopping over 2 degrees of separation. And then our where statement, you can see we want the a.name to be Marion Cotillard, and we want e.name to not be Marion Cotillard, because we want to match all actresses that have worked with her, but not necessarily her. And then again, we want the kind of the production, c.kind, to be a movie, because we're interested in movies that they've collaborated in. And then we return distinct names and titles to return all unique actress movie pairs with Marion Cotillard. In the SQL statement, you can see that now we have like 5 joins that we need to do, because there's another degree of separation that's included in this query. The query is just pretty long now. We have to query 2 cast info tables, the role type table, the title table, and then the name table like twice, because we need to find 2 lists of names, I guess. And then in the where statement, you can see that there's a lot more conditions that need to be held as well. We want the name to match Marion Cotillard. We want to match the role IDs to be actresses in both cases of the edges, and then we want the kind of the production to be 1, which is again movie, and then we want again the actress's name to be Marion Cotillard, or not be Marion Cotillard, to return unique results. And then here is the result of that query. You can see that there's like 1,000 rows, and then a list of all the actresses that she's worked in. Again, it's kind of I cut them off so that it all fit on the slide, and you can see that there's like a lot of people that she's collaborated with. And then I also kind of drew up a kind of visual representation of what that might look like, or at least some of the movies that she's worked with. You can see that there's like that she's worked in movies with like Inception, The Dark Knight Rises, Macbeth, Contagion, and she's worked with people like Gwyneth Paltrow, Ellen Page, Anne Hathaway, which you can see just by scrolling through all the data itself. And she's also had like people that she's collaborated with like in multiple films, like Miranda Nolan worked in both Inception and The Dark Knight Rises, and that might be because Christopher Nolan directed The Dark Knight Rises and Inception, so Miranda Nolan might somehow be related to him. And you can see she's worked with Vera Horton and Eileen Polly in The Dark Knight Rises and Macbeth. And yeah, so I guess since this data is very, very visual, it helps to kind of be able to use a graph database to query it. And then, so those are my examples that I went through, and I'll talk about, I guess, some final thoughts and observations that I might have about this data set. So basically, the further away we get in terms of connections in data, the more joins we will need in SQL. But in Cypher, I guess, if you want to examine, like, say, a neighbor or a neighbor of a neighbor, or even a neighbor of a neighbor of a neighbor, you need to kind of draw a little ASCII thing, like draw another bracket with an arrow pointing to close parentheses for your nodes and edges. And the more tables that are involved in SQL, the more comparisons will need to be made as well. And I just think that at least if in graph databases, it's a lot easier to handle data where the connections are more kind of important. And the SQL queries will become increasingly verbose with each step way that we make. But the Cypher queries themselves don't really, I mean, of course they'll kind of get more verbose too, but not at the same rate as which the SQL queries do. Like, yeah. So thanks for listening to my presentation. Hopefully you found that it was useful or helpful to you, or maybe helped you to see the IMDb data in a new way. And if you want to check us out on our website, you can go visit it at bitnine.net, and then you could check us out on GitHub as well. The AgensGraph on GitHub link is listed below. You can check out the IMDb importing script as well. We have a GitHub link there too. And then IMDb Pi, of course. Check that out if you want to get more information about this very valuable and pretty useful, cool project that I think. Yeah, AgensGraph extension is also on the way. So if you have any further questions, I will hand it back to Aya. And, thanks.
Thank you, Dehowe. Okay, we have some questions. So let me just quickly take a look at this. So again, these are the information for me and Dehowe. So if we don't answer your question today, please feel free, or if you have any further question after today's webinar, please feel free to reach out to me or Dehowe. And also you can go to our website, which is bitnine.net, and this is also a LinkedIn page. So feel free to connect to us, contact us, and we'll be more than happy to support and help you. So some of the questions that we have here, for you is that does AgensGraph support procedural languages? Can we write functions with those procedural languages?
Yeah, it does. I think if PostgreSQL supports procedural languages, then we do as well, because we're forked from PostgreSQL.
Okay, so thank you. And also, we get this question a lot, but it comes up again, so I'm gonna ask you. Can we use AgensGraph on cloud environment?
Yeah, we can.
Okay. Yes. So AWS, I think, is available. AgensGraph is in the marketplace. So at Microsoft Azure, it's coming. Now, the next question that we have is that where can I get the FDW?
The
Foreign data wrapper.
For the foreign data wrapper.
So I think the question is a little bit. So you don't need to get the FDW. So basically, FDW is a part of Postgres. So what you need to do, you need to just activate that extension, and you can just simply use it in case you want to migrate your data from any sources to AgensGraph. Yeah. So for example, is that correct? Yeah.
I think so.
For example, if you have data in your CSV files and you are planning to move your data to AgensGraph, you can simply just activate the FDW extension, and then you can use that extension to migrate your data. And also, I think we have covered it, but we got the question again. So what drivers we have for AgensGraph?
What drivers?
Yes.
Oh, like I think it was ODBC, JDBC, there's like Node.js and Python, just to name a few. There might be more.
Yeah, and also to add to it, we have Golang as well. And yeah, so yeah, that would be all for today. Thank you again, Dehowe. And thank you everyone for joining us today and for being here. And yeah, have a good day. And we'll see you in our next webinar.